And so today I will talk more about the connection between dynamic algorithm and the adversaries. So what you will see, just as I said just briefly last time, we will see the different kind of adversaries, and then just show you the template so far in the literature. How do people design algorithm against each of the adversary? And this is just to remind you that really dynamic algorithm always interact with some guy, right? Like it can be a user, and you also call the user. We also call the user adversary because we think of like this guy to like generate some worst case sequence for us, but the sequence is not always the worst case. But yeah, anyway, we call it adversary. And there are two like big. If you want to separate kinds of adversary, that like you can be fine-grained and make many kinds of them. But the two big thing is the oblivious one and the adaptive one. So the oblivious one is just the one that basically fix the whole sequence of update and queries from the beginning. You can think like it just fixed this sequence. It has some fixed sequence in mind, but just review each of the update and query to you one by one at a time. But this sequence is fixed from the beginning. So this is oblivious in the sense that it doesn't really like see your answer. It doesn't like the next update doesn't depend on what you answer. It's oblivious to that. Then another adversary is just the opposite of that. That is, we say is adaptive. That is, this is a guy that generates the update and query on the fly, in the sense that the next update is generated based on previous answer that it has seen so far. If your data structure returns something, then it might change its mind and give you the next question depending on what you answered. So, for example, you can think like maybe like there are many people who use Google Maps, right? And maybe some people want to go from A to B. Then this Google Map might say, okay, the path is to go through this path P. And because so many people use this path, then it will like it might be the case that okay, now the traffic on path P increased just because this app say okay, you should go through path P. So this is what I mean by adaptive. Like the user might not be adversarial, but it just might be the case that okay, the next update just depends on the answer naturally. And yeah, so adaptive adversary can happen naturally and will happen really a lot in the when you use the data structure inside another static algorithm. So this is like a stronger adversary that you want to work with, usually. And just one term in this talk, I will use the word robust to just say that an algorithm works against adaptive adversary. So it doesn't assume that the adversary is oblivious. Otherwise, we say it's non-robust. Just a word that I will use in this talk. Okay, so far you have seen like a bunch of model of data structure, dynamic data structure now. And so basically the ultimate goal is to design fastest dynamic algorithms that are first, it should be fully dynamic. Also, it should be robust instead of non-robust. And also it should have worst case update time. So usually like in this area, there are so many variants of the model, right? But like you can think like, okay, there is one goal, one holy grail that we are aiming for. And it's a good scientific question, like whether you can give like what is to what extent you can go to this ultimate goal. Can we give some characterization when you can get fully dynamic? When can you make it robust and worst case update time? So inside the dynamic data structure, this is a goal. This is a goal, but just want to make it clear that this ultimate goal is not always needed if you don't care about dynamic data structure itself. Many times we design dynamic data structure so that we want to get faster static algorithm, and all these three things are not always needed. So to like give you an example, I want to tell you one simple example how one can use dynamic algorithm inside static algorithm. And you see that like the strongest model here that we need is not always necessary. That we want is not always necessary. So the example that I want to show is like it's one of the simplest algorithm for computing max flow that I think if you haven't seen it, then I think many people have seen it, but if you haven't seen it, it's quite simple and cute. So let's see what is this algorithm for computing max flow. It is based on a well-known framework called multiplicative weight update. Okay. So what is this algorithm? So imagine that you have a problem where this is a max flow problem. You want to send flow from S to T. And let's say every edge has unit capacity just for simplicity. Okay. So now what you will do first, you will just initialize the weight of every edge to be something small. Okay. And what you want to do is keep doing something as long as the distance from S to T is less than 1. What you do is you first compute some shortest path from S to T. It can be even approximate 1. Let's call that thing P. And when you have the shortest path P, just kind of add this path into your flow. So flow, you can think of it as like a collection of paths, right? So add this path into your flow. And what we do next is just increase every edge on the path by a factor of 1 plus epsilon. And repeat. So note that there is no residual graph at all. You keep working on the same graph. There's like, if the graph is undirected, this is still undirected graph at all time. So keep finding shortest path, increase the weight, and do this again and again until the distance, at some point the distance will be more than 1. And at that point you stop. Then you just return the flow that you have seen so far, just the collection of all paths that you have seen so far. Return that, but you scale down. Just scale it down so that like it is like it respects the capacity. But once you scale it down so that this collection of paths respect the capacity, then that is already approximate max flow.
This algorithm doesn't use the capacities at all, where you stated.
Where would your capacities come in? What's the definition of shortest?
He said capacity. He's doing unit capacity. You can adjust it.
Yeah.
You can change the weight in a different way.
Yes. Yeah. It generalized nicely if you have capacity, the initial weight of each edge will be like this thing, like 1 over this thing times capacity. So if some edge have large capacity, its initial weight will be smaller. And okay, and there will be some small adjustment in how you update. But anyway, this is for like this full thing is for unit capacity graph. So you see that like, okay, this is some nice algorithm. It's simple. Analysis is not too hard, but I will not actually tell you why this gives you approximate max flow. But at least we can see that it is quite fast. Why? Because you can see that the number of iteration will be close to linear in M. The reason is that every edge will be used something like, every edge will be used in the path, at most something like log over epsilon square, actually epsilon square many paths. And the reason is just that every time that you use some edge, its edge increase the weight by 1 plus epsilon factor, right? This increase like exponentially. So after some point, its weight will be more than 1. And once the weight is more than 1, it never will be used in the path of length less than 1 ever. So every edge will be used at most like something like log over epsilon square times. I missed the square, but anyway. And because of that, each iteration you can charge it to some edge. So that would be like something like linearly many iterations. Each iteration you can spend linear time if you compute shortest path from scratch. So that's m squared time total. So that's quite nice, but just from the description of the algorithm, right? It's quite clear that one should be able to improve this using dynamic data structure, like because we should be able to avoid computing this shortest path from scratch at every step. And what do we need from that? Well, what we need is just a dynamic shortest path problem. And the kind of problem that we need is partially dynamic. It's partially dynamic in the sense that all this update is monotone. It's always weight increase. It's not fully dynamic. Also, you only care about amortized update time. If it has good amortized update time, this is fine because you just need to count the total update time from this like single update sequence from the algorithm. But here you see that you at least need the algorithm to be robust because each of the update really directly depends on your answer. It generates adaptively. And indeed, like because like from this thing, like there is like one of my previous work really like implement this robust one that is partially dynamic and have like n to the little one amortized update time, which leads to speed up of this running time from m squared to almost linear. So this can indeed be useful. The dynamic data structure can be used to speed up the multiplicative weight update framework, and it has been used in actually many other examples. So I just want to like kind of tell you briefly that okay, it will be most of the time when you try to implement weight update framework to solve some problem. The kind of dynamic data structure that you need is you usually need it to be robust, partially dynamic, and amortized, like has amortized update time. But if you design algorithm based on some other framework like interior point method, like it will generate like different kind of model of dynamic data structure that you will need. For example, usually when you use integrated point method, you need fully dynamic. And there was some recent work based on some other method. And now it turns out that this framework requires really crucially need that the algorithm must have worst case update time. And yeah, there are like various of method. Some method you don't like. There are some algorithm from geometry and like something about electrical flow. But that's not the point. The point is that the algorithm just makes some list of queries that they want to know non-adaptively. So now all you need is just even offline algorithm. And so my point is just there are many kinds of variants of optimization method, and each of them like leads to different requirements of dynamic data structure. So yeah, you don't always need the dynamic data structure in the strongest model to get good applications.
Question?
Yes.
Just quickly, so in multiplicative weights update, when you say it's only partially dynamic, like you just mean monotonicity, or is there something else?
I really mean monotonicity.
You want to repeat the question, or?
Oh yes, thanks. The question is, when I say partially dynamic here, do I mean like, is it only edge deletion, or I just mean like the update is monotone in some sense? I just mean it's monotone. But usually when the update is monotone, you can really simulate that with like edge deletion only or insertion only. Yeah. Okay. So yeah, there are like the landscape of designing dynamic data structure together jointly with optimization method, I think is worth exploring. Like, it's not just like there is one single goal. There are like it's a rich area. Okay. But yeah, the rest of the talk, at least for this talk, I want to give you at least some templates how people design algorithm that exploit Oblivious adversary, and how to design the one that is against adaptive adversary. Okay, so let's start with the Oblivious adversary one, the non-robust one. There would be two things. Let's start with the first one, which I call the idea is that random point is stable in some sense. So let's see the concrete problem with a full proof. Okay. So this is a dynamic approximate diameter problem, but just for simplicity of presentation, I will actually not work on graph. I will work on metric. Okay. So in this problem, you have, let's say you think of, you have a point set X in a metric D. And you can think of it as like the Euclidean space or something. And this point set undergoes insertion and deletion. You can remove points, you can insert a point. And now the time complexity that I will count is like how many times you need to query the distance between 2 points. Okay. What we want to do is like a kind of decision version of approximate diameter. So we want to return like a yes, no answer. And we want to, if the diameter X, which is just defined to be the maximum distance between any pairs of points. If the diameter of your point set is less than beta, say, some threshold, then you say yes. Okay. And if you return yes, the diameter should be like less than 2 beta. So in other words, if the diameter actually is much more than beta, more than 2 beta, you should say no. just for example, okay, here the diameter is like a 3 beta, so you return no. But now I might delete this node, this point. Now you should return yes. And if I add this point, now diameter is like somewhere between beta and 2 beta, so you can return anything. That's fine. So a trivial algorithm, right, is to recompute everything from scratch, and that takes n square worst case query, like just like compute diameter by querying every pairs. And what I will show you is you can improve this to constant update time in expectation. So let's see the algorithm. The algorithm is that it will at least, let me first state one invariant that is important. The algorithm will try to maintain one point R, and this R should be random. It should be a uniformly random point in your set. And there's one subroutine that I call check all. That is, it just returns yes if the distance from R to everyone else is less than 2 beta. Now we are ready to describe the algorithm. To initialize the data structure, you just start by sample a random point R and return check all of R. If like the distance from R to everyone else is less than 2 beta, you return yes. Now, to support deletion, what we do is just check first if X, the one that you want to delete, is your random point, your root, your R. If that is the case, then you just reinitialize your data structure. But otherwise, your random point is still there. You do nothing. And the last thing is to insert. Okay. And by the way, just to confirm, you should verify that once you delete something, okay, once you handle this deletion, given that your random point was random, after this operation, it will still be a random point in your data set. Okay. If you delete the guy, the R, you resample it. If not, it's just a guy that is not, like, it's still random among the remaining guy. And to insert a point, what we will do is that just to make sure that this point R remain like a uniformly random guy, what you do is like with some probability, which is precisely 1/1 size of your data set, you just switch from just assign your new point to be the R, and then check all. But otherwise, if you don't do this, then all you need to do is just return yes if the new point X is still close to R within 2 beta. So you can see that the invariant that we want really is satisfied, but we really assume Oblivious adversary here, right? So this is crucial, because if the adversary is not oblivious, Yeah, we need this in the running time actually. Yes. Sorry. Let's prove the correctness of this algorithm. Well, if the diameter is less than beta, then there must exist some like a center point such that the distance from center point to everyone is less than beta. But then by triangle inequality, you have that the distance from R to X is at most R, distance from R to C star, and from C star to X. Sum this together, this is less than 2 beta. So it means what? It means that our algorithm will just return yes if and only if the point R have distance like less than 2 beta to everyone else. It will just return yes in this case. And if we return yes, it means that it just means that R is close to everyone within 2 beta, so the diameter is less than 2 beta. So the correctness is clear. Now for time complexity, we will use that like the fact that the point R is random. And okay, first of all, the time to initialize and the time to check all takes linear queries. Just check the distance from R to everyone. What about the time for deletion? Okay. The time for deletion is, okay, first just spend one time to delete. But then, okay, you might need to spend, like, reinitialize your algorithm, which you spend this time to initialize. But this will happen only if, like, the point of deletion is your root, is your random point. But this, because X is independent from R, this is where you exploit the fact that the input is oblivious, like the update is oblivious from R. So this will happen. This probably is just like 1 over X. So this is why like you get constant here. How about the insertion time? Okay, well, with some probability, right, you will assign X to be R. This will happen with probability 1 over X. And then you spend time for check all. But this together, like this is 1 over X, this is X, so it's constant. In other case, you just spend one query. Like in another case here, you just don't reassign X to, don't reassign R. You just use the same R. And you just check whether R is this, just check distance from R to X. That's just like spend one query. So in any case, this is like constant. But note again that this is the place where you need Oblivious Adversary. Okay, so we get that the expected worst case update time is really constant. And just to conclude, this simple algorithm gives you constant update time in expectation. Okay, this is simple, but I want to point out that this is really the template that is used by tons of non-robust algorithm. The template is that you usually you spend a lot of time to build data structure based on some random point. And you might need to rebuild it, but you will need to rebuild it only when this random guy is affected. But this random point is stable. It's stable against an Oblivious Adversary. Because R is random, we don't need to rebuild often, right? Because intuitively, Oblivious Adversary, like R is some random place, but Oblivious Adversary doesn't know where R is. So it might affect your data structure here and there. But it takes long time before it really affects R. So R is unaffected for long time in expectation. That's why you don't need to rebuild your data structure too often. And this template has been used by many other algorithms maximal matching, spanner, maximal independent set, and many others. Yeah.
So this algorithm does have some robustness, right?
No.
Because even if the updates are adaptive, if you only get the yes/no answers, how will the adversary know to hit R?
Okay, so the question is that good. That's a quite good question. So the question is, because we only return yes and no, so it seems like the adversary doesn't know where R is because we just give yes and no answer. That's a good point. However, there is some place where the adversary could learn a bit about R. This is the place where when the diameter is between beta and 2 beta, this is the place where you might return yes or no. And this answer will reveal some information about this, the inner configuration of your data structure. It's not clear how effective this revealing is, but it will learn something.
In this middle range where you give out information, can you just put what coin that you can give out?
You don't know.
You don't know your.
But we're all feeling like there's something here, right? Maybe there's another category of, not oblivious adversary, because it does seem like, right? It seems like this is very low opportunity, small opportunity. Is there some kind of middle ground or some kind of characterization?
So the question is there some kind of model of adversary that we can define and say that this algorithm that you just seen still work against that? Maybe that adversary is not completely oblivious. That's a good question, and I'm not sure. Yeah.
Just towards that point, correct me if I got this wrong. I thought it's not universal when people say adaptive adversary if they mean seeing the output or they mean seeing the internal randomness.
Yeah.
And the term is sometimes used for both cases.
Oh, really?
So, yeah.
But for this talk, it's always the former, just to make sure I
For
understand.
this talk, I always mean that adaptive adversary only sees the output. But sometimes people use the term non-oblivious to mean that it really sees everything inside. Yeah. But when you think of using data structure that interact with the static algorithm, usually the static algorithm can only see your answer, and it doesn't try to pry into your internal randomness. That's why.
I've been in that situation quite frequently, and the question is really, when do we have a proof against an adaptive adversary, and when don't we? I have approximate min-cut algorithms that are sort of the same flavor, and it seems really hard to prove you can't do it, and then you try to resort to differential privacy and stuff like that. But yeah.
Right.
Sorry, one more.
Yeah.
What is known for this problem against adaptive adversaries?
Very good. So there was a recent paper from Soda, this Soda, which shows how to get full approximation. I'm not sure if you, but they solve a much harder problem like a case center, which is just generalization of this one. This is just one center problem. I'm not sure if you really focus on diameter, can you match two approximations? That's a good question. Yes,
One center is radius, not diameter.
one center is radius. Oh, I see. Yes, thank you.
It seems like he's been discussing, probably this radius, right?
Yeah, yes.
It's, yeah.
But the other is the same algorithm to work. You modify it.
Mhm. Okay. Yeah. So I missed the definition of the problem, but let's go on. Okay. The next template that is used quite like not as much, but very interesting though, is to use linear sketch in the data structure, and this has been used in dynamic algorithm. I think for the first time that is best to my knowledge by King, Capron, and Mountjoy for worst case dynamic connectivity. The first algorithm that gives worst case dynamic connectivity in polylog time, it used some linear sketch. And but there are some other algorithms too that use linear sketch. But the point is, and you'll learn more about linear sketch, I think, tomorrow for the whole day. And the thing is that linear sketch usually inherently assume Oblivious adversary because it uses some hash function. And the random choice of how you generate the hash function randomly, you want to hide that random choice, how you sample the hash function. But anyway, just want to point out that trying to get linear sketch against adaptive adversary is currently actually one of the intensively studied topics in the streaming community area as well. So it's quite interesting to see whether there will be more synergy and new development in this direction. Now I want to switch to the robust one. How do people design algorithm for against adaptive adversary? And there are at least right now I can see 3 things. One is unique answer, kind of deterministic almost. Yeah. Another one is the opposite, to be noisy. And there are some other ad hoc way to do things. So let's start with the first one. So unique answer imply robustness. What do I mean by that? I mean that suppose that you promise that your algorithm work against Oblivious adversary, but actually, if the answer of this algorithm actually is just uniquely the whole sequence of answer from this algorithm is uniquely determined by the whole sequence of updates. Think of deterministic algorithm. But it doesn't need to be deterministic. If your answer is just determined by the whole sequence from the update sequence, then I claim that this algorithm itself actually already works against adaptive adversary. There's nothing deep about this, but let me just argue quickly. So suppose for contradiction that actually this algorithm A doesn't work against adaptive adversary. So there is some adaptive adversary B that can generate, that can interact with A and then generate the update sequence such that at some point the guarantee of A fails against this sequence U. Okay. Now once you have generated this update sequence U, let's fix this sequence and say that, okay, now I'm gonna define another Oblivious adversary B prime. This B prime will just work with A by fixing this update sequence U and feed the update sequence U to A one by one. And this is a fixed sequence now. So this is Oblivious adversary. But what will happen when B prime feed up this update sequence U to A? A must behave exactly the same way, just because the answer of A is determined by the update sequence, right? So it means that, okay, because answer of A is uniquely determined by U, A must fail again against B prime. So A actually fail against Oblivious Adversary, and that's contradiction.
Are you assuming determinism here?
No. Like if I don't assume determinism, like here it will be true with high probability. So I assume if I don't assume deterministic here, then like I need this to be like with high probability.
But could you sort of achieve this by modifying the problem? As an example, looking at the looking at the radius problem. The question was, give me an estimate of the radius rather than given the threshold. Rather than giving you the answer, if I force my algorithm to only answers on powers of I, powers of 2 within a factor of 2, then it would be that the answers are determined exactly by. Like, could you modify the problem to make sure that the answers?
I am not sure if I get your question.
So
actually.
let's consider the radius problem, right?
Yes.
I could frame it as give me an approximate radius.
Mhm.
Okay, but that by itself like would not fall under this problem. But now I can say, okay, like I allow you to answer me a power of 3, right? Once you are a 2 approximation, a power of 3 is unique, or let's say power of 2, right? Just to get the number strictly right. You have to answer, but then it would fall under this framework, and you would get a determinist. Like the answers are uniquely determined by the input, and hence you, with a slight modification, you will actually have an algorithm that works against adaptive adversaries. Am I getting this right?
Yes. Mm-hmm. So I think the question is like, can you like? Is it the case that if you have an algorithm that works against Oblivious Adversary, and you can just adjust the problem slightly so that the answer is naturally unique, then you would get algorithm against adaptive adversary. The answer is yes. Yeah. Once you just change the problem definition such that any correct algorithm must return unique answer, then you get adaptive again, the one against adaptive
But the
adversary.
problem gets much harder because then you have to know some threshold.
Yeah, so I'm assuming there's an algorithm that works for, like, actually gives you a radius estimate, let's say, right?
Yeah, but also there will be a certain radius for which it has to give a specific answer if you want to make the answer unique. Then there will be a certain threshold where where it's clear where you need to know the radius exactly in order to be able to do a correct rounding. So you make the problem much harder. That's what I'm saying.
I see.
Yeah, so like the generic answer that I just answered Sushan holds for this specific problem about radius that we have seen. There will be some like concern about where exactly do you round, and that threshold of rounding will be like still might reveal some information to adversary. So for this specific problem, it's not that clear, but the generic answer is fine. Okay, now like how do people get unique answers? Right, there are several ways to say that algorithm is uniquely determined by the updates. Well, the classical way, and like many people just do this just to make algorithm deterministic. That's the classical way to make algorithm robust. And if the answer is Boolean and it's not like there is no gap like the radius problem that we have seen, like so if the answer is Boolean, yes or no, there is no like a gap where you can answer anything, then the answer must be unique, because if your algorithm is correct, the answer is uniquely determined at every step. So every correct algorithm for decision problem without this gap is just automatically robust.
More generally, if you give exact answers, right?
If you give exact answer, you are robust. And if your algorithm is like the answer is unique or like a pseudo-deterministic in a sense, like maybe you want to maintain a spanning tree, but what you do is you return a minimum spanning tree. And minimum spanning tree, at least in the graph that has distinct weight, is unique. So in this case, like your answer is unique from the definition, or you might return the residual graphically first one, or for any problem. If that is the case, then you are robust. So any of this is robust. Okay. So that's like the classical things to do. But let's look at another one, which is newer. It's kind of the opposite one. Like instead of being unique, there's one thing. Now you're being noisy. The high-level idea about this second approach is just that when your answer is noisy enough, then the noise actually prevents the adaptive adversary from learning your internal configuration. Okay? And this is actually formalized and formalized through the connection to differential privacy and adaptive data analysis. These are the two areas that we have used the insight from. And so let me tell you, at least I will state like the nice black box transformation that works. Okay. So
Connection. Please try again later.
there will be there is like the black box transformation that works for any dynamic value problems. So what do we mean by that? I just mean like the problem where like for each query you return a single number, but that implies a lot of problem, like dynamic distance oracle, where like you at each query you get S and T, you want to return information like the value of ST distance or the value of ST min cut. This is the dynamic value problem. Or dynamic global min cut, what's the size of global min cut right now, or approximate size of global min cut, or approximate diameter, and so on. Okay. So these are all dynamic value problems. Okay. So I'm gonna tell you what is like the black box that transform any non-robust algorithm for dynamic value problems to the robust one. And actually, if you don't care much about efficiency, this is easy to achieve. Because let's say you have some problem, which is dynamic value problem P, and there is some non-robust algorithm against Oblivious adversary. And let's say that it can handle, this algorithm can handle up to T updates. To get a robust algorithm, all you need to do is just make T copies of this non-robust guy. And then let's say that your new algorithm just return the answer from the ith copy on the ith query. Okay. So this now will be robust. And the reason is just because the randomness from AI, okay, this random configuration of AI is leaked at step I, but we never use it again. So that's fine. Okay. So, but like you see that the update time increased by a factor of t, where t is the number of updates. Now, what is now known is that this can be improved. So now let me tell you what is the improvement. It's gonna be very similar. Okay, you have a problem P, and you have a non-robust algorithm that works up to t updates. I'm gonna just make, instead of t, make root t, many copies. And what we're gonna do is just to return kind of noisy version of the median of these copies. And so it's like you just compute the query this guy, look at the median, actually look at like approximate median and try to like add a bit of noise, precisely exponential noise. And but doesn't matter too much what exactly is this noise. It's just some noisy version of median. And one can prove formally that now A prime is actually robust. I hope to give this full proof in the next workshop. But for today, I just hope like for you to see that, okay, the noise, adding noise actually is one generic way to transform non-robust to robust algorithm. So, so you see, this is like a saving factor of root t. So that's quite nice. And by the way, like one can reduce the number of query because here, like at each time step, actually we queried C many algorithm, but you can reduce the number of query per step from C to polylog just by, instead of return a private median of everyone here, just sample log n many guys here and return the private median of the guy that you sample. That will work too. Okay.
Is square root t good enough in various things? Because that's typically quite big, no?
Yeah, it's quite big, but like similar to what you have. So okay, so the question is like whether square root t is good enough for application to get anything useful at all. The answer is yes. For example, Mikhail mentioned that he has algorithm for returning approximate min cut in root n time using this black box together with this idea. You get approximate min cut algorithm with update time something like n to the 3/4. So something sublinear, but it's going to be slower.
And just to add, this is a situation where nobody would know how to use the information of min cut that my algorithm has. I mean, so that's why we have to go through all this extra cost just to get a proof, right?
Yeah.
Is there a lower bound on the number of copies that you need in terms of T?
So there is a lower bound. So the question is that is this tight?
Yes.
And the answer is tight for this approach. I'm not sure. Actually, yeah, it might. Like people in privacy and adaptive data analysis might actually, they might know by now, but I'm not sure. Okay. So these are like the two generic way. Now let me tell you there are something to explore. And so, okay. To tell you about this, let me give you simple algorithm for this problem of edge coloring. The problem is that you have a graph that undergoes edge update, and let's say that this graph has small, maximum degree of delta. Maybe delta is not too small actually, but it has maximum degree of delta. And what you want to do is to maintain the edge coloring. such that any adjacent edge doesn't have the same color. So these two edges they share the vertex, so it cannot be the same color. And let's say I just want to use at most 3 delta colors. You cannot use less than delta color for sure, but here we use 3 delta colors. And the worst case update time is trivially you can do it in delta worst case update time, but we're gonna do it in constant in expectation. The algorithm gonna be quite simple. So first of all, let's say that for each vertex we maintain a set of color of edges incident to it first. And okay, we can given edge update, we can update this set in just a constant time. And actually we're gonna do this too. That is, given a color, we want to be able to check whether this color C is in this set in constant time as well. To implement this in constant time, you can use array. But if you don't care about constant time, you can use binary search tree and pay log n. That's not the point here. Okay. Now what do we do? When you delete an edge, you don't need to do anything. The valid coloring is still valid. What about insertion? What I'm gonna do is just here.
But after delete, you still need to update the round.
Yeah. We keep updating this. Yeah, right. So, but it's gonna be constant time. Yeah. Good point. To insert, we update this too. But what we're gonna do is, I'm just gonna sample a color to this edge UV. Color it from this color, this palette of size 3 delta. You color it and check if this color is valid. That is whether this color is in around U or around V. If it's not, then it's free. Then you use it. If it's not free, then use resample. So the correctness that it maintains an edge coloring is clear. And how to see the update time? Well, let's just try to analyze how much you need to resample, how many times you need to resample. Well, the number of the insertion time is just how many times you resample, because each time that you resample, you can check whether the color is free in constant time. But in expectation, the number of resample is just 3, right? This is just because the probability that this color is not free is just at most the size of around U plus the size of around V over your palette size. But around U and around V have total size of 2 delta at most. And your palette size is 3 delta. So this is less than 2/3. So the number of resampling is just a random variable which is a geometric that followed geometric distribution of success rate at least 1/3. I'm gonna finish soon, but yeah. So yeah, expected insertion time is constant. So it's a simple algorithm, and let's reflect just quickly why is it actually robust. It's randomized, but it's still robust. And this is because you see that randomness is purely used to speed up the insertion time. It's just used only to pick some color that should be nice for you. It doesn't need assumption that your solution follows some distribution. There's no point of time where you assume that the thing that you have maintained from the past follows some distribution. No, it can be anything. It's just that at this current time, I want to pick something quickly so that it's to speed up the update time. Okay, there are more ways to robustness. There was new techniques that I call proactive resampling. It has been used in 2 papers so far, but I hope that it might be more useful. And the rough idea is that the idea is like we try to work with adaptive adversary, but usually adaptive adversary can mess with you in the sense that it can try to force some bad structure. But what we're gonna do is like whenever adaptive adversary might create some bad structure to you, you just kind of resample that part and make this bad structure disappear. Very vague, but you can have a look. Another thing that is interesting and it has been used in this new MaxFlow paper, almost linear time MaxFlow, is that they designed the algorithm that they designed the approximate mean ratio cycle dynamic version, but instead of design the one that have good approximation, they just want to design the one that is competitive against stable solution sequence instead of optimal solution sequence. So kind of they relax the approximation guarantee and don't compete with don't try to be optimal at all time, but just try to be competitive to something that they call stable. And once you do that, you can maintain something that is still nice and maybe not optimal, but nice enough for the application. In any case, I think we really need more theory on how to design robust algorithms, and I think it's like interesting venue to explore. Yeah, thanks a lot for today. Yeah.
Thank you. Questions?
So thanks, Thatchaphol. Very nice survey. So just you actually use proactive resampling in the radius one, right? Like we were resampling whenever a new point came in with some small probability 1/x.
You might think of it like that. I'm not sure how to make that algorithm really works against adaptive adversary formally, but here, when I say I use proactive resampling, it's really work against adaptive adversary.
If I followed correctly, I guess in the diameter saying we're resampling when it really broke, and in that paper you're sampling where it's not broken yet, but like it might break later.
Yeah.
I thought the description actually had a resampling even when it was not broken, but I know it would not work against adaptive. I think you had a sampling even when it was not broken.
Right.
I see. Thanks. More questions?
I thought you had something in TAT about inverse maintenance, which is some noisy thing.
Yes.
It
So
would
what is
fall,
that?
I think, under the umbrella of the add noise.
Add noise.
I enjoyed your taxonomy.
Okay. So it falls under that umbrella?
So, yeah, it is like, so there are 2 papers that use noise right now. Wait. This one is the black box statement that I state. This one, by Aaron, Yintat, and others, they add noise too. But like I didn't talk about it.
So, if I may. Yes, there are a bunch of different, I think, strategies for adding noise. I think this use of differential privacy with a collection of them is one very nice one. The inverse maintenance paper you do a trick where you estimate something so precisely that if you like add a little bit of a nice distribution, the resulting distribution is like close to what the distribution would have been if you had exactly computed an add noise, and they're like not distinguishable. So it's still in the broad family of add noise, but maybe a different way of reasoning about the effect or the kind of indistinguishability from adding that noise. Is that?
Yeah.
I can talk offline about more ways of hiding randomness in optimization methods. But more questions for Thatchaphol. All right, well, thank you again. We have a break now until 3:30, and I'll be back for the last talk today.
And there's tea upstairs.
He's upstairs. Okay, thank you.